Okay, so today we're going to be doing the quadratic formula again, but this time the discriminant is not going to be a perfect square. I'm going to get irrational roots. And remember, if we get irrational roots, like let's say the square root of 20, we're going to break that down into whatever roots we can. So if I get, let's say 4 and 5, I can take the square root of 4, which is 2. I cannot take the square root of 5, and I'm going to leave that behind. And we're going to get some aspect that looks like this. And the cool part about irrational roots is that if one's irrational, so is the other. Because remember, we're looking for the distance. So if I know the distance over here is some sort of square root, I know the distance on the flip side is also going to be a square root. One irrational root comes with a pair with another irrational root. That is a general rule that will be applied. So each one of these is going to have 2 irrational roots. So let's go ahead and get started. The same process applies today as yesterday. We're going to take the quadratic formula, which is negative b over 2a, and we're going to add and subtract the discriminant, which is b squared minus 4ac. I'm going to take the square root of that. All we need is I need to know my a, my b, and my c. A is the number in front of x squared, b is the number in front of x, and c is the number with no x. So let's go ahead and plug that in and see how we do. So negative plus or minus 4ac over 2 times a. So that's a negative b plus b squared minus 4 times a times c all over 2a. So it's negative 8 plus or minus, let's see, that's a 64 minus 44 over 2. Oh, lo and behold, our first example is going to be the same thing as up here. So x equals negative 8 plus or minus the square root of 20 all over 2. And so what we're going to do is we're going to take a quick pause and take the square root of 20 and see if we can't reduce that. We already know that 20 breaks down into 4 and 5. I can take the square root of 4, which is 2. I cannot take the square root of 5, so I'm going to leave that. So I'm going to rewrite this as x equals negative 8 plus or minus 2 square root of 5 all over 2. And then the last thing that we're going to do is we're going to check out, hey, I'm going to use blue for this, can I reduce this fraction? And the answer is yes. Both 8 and 2 both divide by 2. So negative 4 plus or minus 1 square root of 5. Now, with this, typically speaking, this is going to be where we stop. You could split it, but remember, this doesn't reduce any further. So if you split it, you're just going to be writing out. Let's split this. So that would be x equals negative 4 plus the square root of 5, which gives me that right root. And x equals negative 4 minus the square root of 5, which is going to give me the left root, which is no different than what we were showing right there. So let's do one more of those. So what we need is I need to know my a, my b, my c. A is the number in front of x squared, b is the number in front of x, and c is the number with no x. I'm going to plug it into the formula, which involves taking the vertex and then adding and subtracting the discriminant. There we go. Let's plug in our values. Negative 8, 8 squared, negative 1, 15, negative 1. If we start simplifying this, it's going to be a positive 4 times 15 is going to be a positive 60. Okay. X equals negative 8 plus or minus the square root of 124 all over negative 2. And again, we're going to take a quick pause. Square root of 124. We're going to break it down. So I noticed in this case, 4 goes into 12 and 4, which is going to be 31. I can take the square root of 4, which is 2. I cannot take the square root of 31, which means that that can be broken down into x equals -8 plus or minus 2 square root of 31 all over -2. We're going to ask ourselves if I can reduce both the tops, and yes we can. X equals -8 divided by -2 is going to be a positive 4. 2 divided by -2 is going to change the sign. So you can either leave it as plus minus because I'll still have a plus minus, or if you want to be super fancy, you could say minus plus. Really, there's no difference between minus plus and plus minus. You have one of each. If you wanted to split it, basically what would end up happening was you would have an x equals 4 minus the square root of 2 times 31. Oh, hold on. 2 doesn't exist because 2 divided by 2 is 1, which means that this doesn't exist. It's just 4 minus the square root of 31. And my other one would be x equals 4 plus the square root of 31. You have your two answers. There we go. So I want you to take that as an example. I want you to pause the video, try out number 5, resume it when you're done, and see how you did. Okay, so let's get down our A, our B, and our C. We're going to plug that into our quadratic formula. Okay. My B is -9, my A is -1, and my C is -17. Perfect. My -9 is going to be at +9. See, that's 81. -4 times -1 is +4 times -17 is going to be negative. Let's see, 2 times 17 is going to be 34. It's going to be 68. Perfect. X equals 9 plus or minus square root of 13 all over -2, which in this case, I can't reduce 13 like we did before, so it's just going to stay that. Awesome. So let's get just a few more. Let's do 2 more of those, make sure we got the process down. So again, the big thing that you're going to be doing is you're just going to be finding your A, your B, and your C. A is in front of the x squared, B is in front of the x, and C is the number without x. And you're going to plug it into your formula, which is your vertex, -b over 2a, and you add and subtract the discriminant, which is b squared minus 4ac. In this case, I get -16 plus or minus 256 minus 4 times 3 is -12 times 12 is -144, which in this case is, let's see, that's 1, 1, 2. Okay, so we're going to take a pause and find the square root of 112. Let's see, I know it's even, so I'm going to divide it in half, which is 56, which is 7 and 8. This looks like a split table, so it's 2 and 4, so I'm just going to go ahead and split it all the way down and circle my pairs instead. Cross out a pair, cross out another pair, which means 2, 2, and the 7 stays behind, which is 4 square root of 7. So the 7 stayed behind, my 2's canceled out, and my other 2's canceled out. So I have x equals -6 plus or minus 4 square root of 7 all over 6. I notice that I have some reduction that can go on. X equals -3 plus or minus 2 all over 2. There we go. So for the last one, go ahead, pause the video, give it a shot, resume it when you're done, see how you did. Let's see, A, B, C. Plug it into your formula. And simplify. Don't forget a negative b is a negative negative. It's positive 12 times negative 12 is negative 144 over negative 6. There we go. In this case, I can actually split. I guess we had a real one slip in there. So I have an x equals 13 plus 5 over negative 6. X equals 13 minus 5 all over negative 6, which gives me 18, which is negative 3. And negative 4/3. And there we go. So today we're going to be simplifying radicals. And a really good first start at simplifying radicals is typically shown in the book by perfect root factor trees. I like this idea. The only problem is that if you don't spot the perfect root factor trees, which means you're dividing by one of the perfect squares, like 1, 4, 9, 16, 25, if you're not dividing by one of these numbers, you don't tend to spot it. So what I like to do is I like to build what we call split factor trees. And the idea is the fact that you're going to take any one of these numbers and you're going to factor down into its prime number forms. If we have any numbers that can be divided further, those are what we call composite numbers, you keep going. And then you basically list what factors that you have in either pairs, 3 of a kind, or 4 of a kind, depending on what type of root it is. So on this side, let's go ahead and let's try just building a basic factor tree. If the number is prime, circle. If the number is composite and can be factored further, square. And really at the end, we're not going to square up numbers, we're just going to circle our primes. So let's go ahead and take a good start. So 2 numbers multiplied together to give me 30 are going to be 5 and 6. 6 can then be divided further into 2 and 3. So when I list my answer as a set of prime numbers, I know there is 1, 2, there is 1, 3, and 1, 5. So I'm going to list my answer as 2 to the first, 3 to the first, 5 to the first in ascending order. Not too bad. If I did something a little bigger like 72, well, I've kind of forced you into a certain set of avenue. I can't divide it by 2 and 36 because 2 would be prime. So I'm going to have to go with something a little larger. How about something like 9 by 8? 9 I can factor down into 3 by 3. 8 I can factor down into 2 and 4 can be factored down into 2 and 2. So going with my prime numbers, I'm going to go, I have 3 2's, so I have 2 to the 3rd power times 3 to the 2nd power. That gives me 3 2's and 2 3's. Perfect. And so the whole setup here is, again, we're not going to box up our composite numbers, but we're going to circle our prime numbers. So if I take a number like 108, I can factor this down in any two numbers, and I'll get to these. So if I wanted to say, let's do 2 and 54, that's prime. If I broke down 54 into 2 and 27, well, that's prime. 3 and 9, well, that's prime. 3 and 3. So my answer here, let's see, I have 2 2s, so 2 squared, and 1, 2, 3 3s. So 2 2s and 3 3s. So that's my answer. The cool part is it doesn't matter how you break it down, like we said. If I broke down that 108, let's do it a different way. 108. Let's instead break that not by a 2, let's break it by, let's say, a 6. If I broke it down into a 6, see, 6 fits into 10. 1 time with 4 left over, 48. That would leave me with, sorry, brain lapse here, 8 times. So I get 6 and 18. If I broke down that 6 into a 2 and a 3, those are prime. The 18, I could break that down into a 6 and a 3, prime, 2 and 3, prime. Needless to say, this is a very different breakup than what we had right there. But again, I have 2 2s and 1, 2, 3 3s. So it doesn't matter how your factor tree is broken, you'll get the same factors. So what I want you to try is I want you to try number 7 and number 9 on your own and see if you get the same final prime factors as we're about to show here. Again, it doesn't matter the path, just see if you can get to the same final factors. Okay, so let's take a look. So the number 28, I'm going to break that down into a 4 and a 7. 4 I'm going to break down into a 2 and a 2, both of which are prime, and 7 is prime. So I know this is 2 to the second power times 7 to the first power. So there we go. 36. A couple ways we could break it down. A lot of you might have gone for 6 and 6, but I'm going to take the longer way just to see if I still get the same answer. I'm going to break it down into 2 and 18, prime, 2 and 9, prime, 3 and 3, prime. So I have 2 2s and 2 3s. How'd you do? Well, this idea right here, building a factor tree, is one of the most critical aspects of simplifying radicals. And I think that a lot of people get scared, or maybe they haven't seen some of the deeper process on what's going on here. I'm going to ask myself, what number multiplied by itself gives me 225? Some of you might be able to spot and say, that's 15. But for larger and larger and larger squares, oftentimes we don't actually recognize them, and we have to kind of figure them out the longhand version. And so let's build a factor tree to simplify this radical. And a couple rules we want to remember. If I'm looking for a square or the redundant square root, I know that I'm looking for 2 of a kind, so I'm going to call it 2 oak. So 2 of a kind for those types of roots. If I have a cube root, which means there's a 3 tucked up in here, I'm looking for 3 of a kind, so 3 oak. And if I have a 4 tucked in there, that means I'm looking for 4 of a kind. Couldn't draw the letter K for some reason. So when I build my factories, I'm looking for pairs. I'm looking for 3 of a kind and 4 of a kind, because what number multiplied times itself 4 times gives me this? So I want to find that factor 4 times. Or likewise, what number multiplied by itself twice gives me that number? So I'm looking for 2s. So if I take a number like 225, I'm going to break it down into, I recognize that it ends in a 5. So I'm going to say 5. 5 fits into 20, 4 times with 2 left over. 5 fits into 25, 5 times. So a 5. 45 is also divisible by 5, which gives me a 9, prime, 3, and 3. So I'm looking at 5 squared and 3 squared. What number multiplied by itself 2 times? So I'm looking for groups of 2. So I'm going to cross out that group of 2 and know that I can pull out a 3. So what number multiplied by itself twice? 3 is multiplied by itself twice. What other number multiplied by itself twice? 5. So I know my final answer is whatever 3 times 5 is, which is going to be 15. Boom. So even if we don't make it straight to 15, we still get there by saying, pull out a pair, pull out a pair. Likewise, if I have something like this, I'm looking to do the same thing, but I'm looking for 4 of a kind. So when I take that root, let's say 4 and 4, 2, 2, 2, and 2. So what number multiplied by itself 4 times gives me 16? Well, 4 times is a 2. So my answer, what is the 4th root of 16? 2. Awesome. So let's try one that maybe doesn't simplify down to a perfect value. Now I've got some out here. First off, I know that if that 5 is outside of the root, it's not a 5th root. That's just 5 times the square root of 700. So my answer is going to be 5 times whatever the square root of 700 is. And we're going to have to figure that out. So I'm going to break down 700. The easiest way that I think is to break it down into 7 and 100. Let's see, 2 and 50, 2 and 25, 5 and 5. Okay. And so again, we're going to ask ourselves what number multiplied by itself twice gives me this. So twice a 5, twice a 2. Unfortunately, the 7, no number multiplied by itself twice that is rational will give me a 7. So I have to leave the 7 in the root. I can't actually pull it out. I'm going to attempt to simplify as fully as I can like I did up here, but in this case, I can't do it. I'm going to multiply 5 by 5, which gives me 25, times 2 is 50. The answer to this one is 50 times the square root of 7. Boom. There we go. And again, this works the exact same way if I have a 4th root. I'm going to break this down into 162. Don't really know where that's going, but I know it's an even number, so I'm going to break it down into 2 and 81. That's prime. 81 is 9 and 9, and both 9s give me 3s. So again, when I start pulling things out, I'm looking for what number multiplied by itself 4 times, which means I'm pulled out a 3, but don't forget, whatever I'm pulling out, I am already planning on multiplying by 4. So I pulled out a 3. I can't do the 2, so I'm going to have to leave the 2 there, but I'm not done pulling things out. I have a variable, t to the 5th. So 1, 2, 3, 4, 5. How many t's? Well, what number or what variable multiplied by itself 4 times? Well, got 4 of these right here. Just like I had 4 3s, I have 4 t's, so I'm going to pull out a t. What didn't I pull out? A 2, so 4th root of my 2. What didn't I pull out? A t. So do we see where we pulled out some of the t's, but not all of them? So 4 of a kind, I pull out a t. The 5th one doesn't have 4 of a kind to pull out, so it stays. So I say 4 times 3 is going to give me 12. That's the 4th root of 2t. Perfect. And so let's do a couple more that kind of revolve around that concept. If I'm looking for the square root, again, I'm going to break this down into, I know it's an even number, so 2 fits into 19 9 times. For 18, which would be 1 left over, 2 fits into 12 6 times. 96, I know that that is divisible by 3, so 3 fits into 32 times. Oh, 32 is something I can work with. How about a 4 and an 8? Those are 2s if you believe it. The 8 breaks down into a 2 and a 4, 2 being prime, 2 and a 2. Awesome. I also know that I have 2 x's. So my process is going to list all of finding pairs of numbers. So I have a pair of 2s, 2. I have a pair of 2s, so 2. I have a pair of 2s, so 2. I also have a pair of x's, so x. What I don't have a pair of is 3s, so I leave the 3 behind. So 2 times 2 times 2 gives me 8x square root of 3. Perfect. Sometimes you can't bring anything out. So like on this example, If I break down my 16 into a 4 and a 4, which breaks down into 2s, I have 1, 2, 3, 4, 5 x's and 1, 2, 3 y's. I'm looking for 4 of a kind, which means I know I can bring out a 2. I'm looking for 4 of a kind, so I know I can bring out an x. But I can't actually bring out any y's. So I'm going to have to leave behind both the 4th root of an x and all 3 of my y's, which that, conveniently enough, is the answer. 2x times the 4th root of xy cubed. Awesome. So take what you've seen on this, and I want you to try number 10 and number 12 right there to see how well you do. Unpause the video when you're done to see how well you did. Okay, so what I've got here is I noticed that my square root has a little 2 in there. That's kind of a redundant setting. It's almost like saying I have x to the power of 1. We don't actually need to write the 2. We know that that is a square root. So we're going to be finding pairs of numbers. So I know that my answer, I'm going to have to multiply whatever it is by 3. I'm going to break down 15 into 15 and 10. So 3 and 5, both primes. 2 and 5, both primes. My b, I have 1, 2, 3, 4, 5, 6, 7, 8. Looking for pairs of numbers, so I see, let's see, a pair of 5s, so I'm going to pull out a 5. I see a pair of b's, so that's at least a b. That makes it b squared, b cubed, b to the 4th. If you wanted to do that the long way, you could write b, 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 b for each b that you write out, but easy enough, it's just b to the 4th. Last thing we're going to do is we're going to write that 3 is left over on the inside. Again, we don't actually need to write the 2 because it's a redundant setting, but that would be what it would look like if we had a 2 in the root power. So we have 15 b to the 4th times the cube root of 3. Perfect. And on number 12, kind of doing the same thing. I have 9 and 9, which is 3. All these 3's, I have 1, 2, 3, 4, 5. And I have 1, 2, 3, 4, 5, 6. So I know whatever my answer is, I'm going to multiply by 4 for that 4 that's sticking out there. And I'm looking for what number multiplied by itself 4 times. So 4 of a kind. 3. Let's see, I have 4 g's right here. And I have 4 h's. Unfortunately, I couldn't pull out the g or those other 2 h's, so I'm going to leave them behind, and I'm going to simplify this into a 12 gh, 4th root of gh squared. And there we go. So today we're going to be working on numbers on the complex plane. And so what the complex plane is it involves an area called lateral numbers. What we are used to up until this point is numbers that either go in one direction or in the other. We have what we call the positive and the negative axis. You either have more of something or less of something. What we're introducing when we say the complex plane, we're now saying, hey, we can have something else. And what this means is that, let's say you have 2 apples, and I have 2 oranges. If I have 2 and you have 2, we both have 2, but you don't have more fruit than me. You have a different type of something. I can take your apples away, but that doesn't necessarily add to my value. We're looking at, and that may not be the best analogy, but the idea is we're comparing something new, something that's still 2 units away. You're still 2 units away from being hungry, but we're not in the same direction. You have an apple, I have an orange. So we're introducing a second dimension to the number line. And this is what we call lateral numbers. Now, the fun part is a lot of students ask, well, why does I represent a lateral number? Why wouldn't L represent a lateral number? They almost look the same. Why use an I? Well, that comes from way back when mathematicians called Rene Descartes when they were first looking for what is the square root of a negative number. They were looking at quadratics and how they work out, and he said, hey, these things are impossible. You might as well call them imaginary. Along several other things, and several other mathematicians said, I cannot find a use for this thing. Why don't we just say this is stupid? It's imaginary. It's impossible. You can do this math, but it doesn't mean anything in the real world. So they started denotating it as I for those impossible imaginary numbers. A couple centuries later, we come around, we find that in fact these lateral numbers have many different uses, especially when we go down to quantum mechanics in the quantum realm. A lot of different forces use things that represent lateral numbers. A lot of computer programming use them as well. So, albeit in his time, René Descartes said these are impossible, I will never find a use for them. We have in fact found that this is a highly useful skill, especially as computer software is developing. So it's worth figuring out, how do numbers work in the lateral plane? So let's take a look. Whole idea is I is the square root of -1. So if I have I squared, I will get -1. That's the idea. So whenever we break down any sort of square root, typically we would break it down into two different square roots. I'd say, okay, a -49, I'm going to break this down into the square root of -1 and the square root of 49, both of which I can find values for. The square root of -1 is going to give me I, because what number times itself gives me -1? I. When I say what number times itself gives me 49, I get 7. So my final answer is 7I. Boom. Likewise, if we don't want to break it down into just two, let's say 98. 98 isn't a perfect square, so we're going to have something left over. So first off, let's break down 98 into the square root of -1 and the square root of 98. Now 98 I can divide by 2, so I'm looking at the square root of 2 and the square root of 49, of which I know the square root of -1 is I know the square root of 49 is 7, but unfortunately I can't reduce down my square root of 2. So in this case I have a 7 and an I with a leftover square root of 2. Now, the same thing works for these numbers as do variables. If I have variables in here, most of the way that we're going to break these down is by factor trees. Now, I'm not going to write out the square root each time. Typically, the way that we write these out is we would write them out as a -1, a 16, and then the older fashion for these variables is I would write out an x and an x. What I would do right here is I would say 4 and 4, and I would circle pairs of numbers. Okay, the square root of 16 is 4 by 4. I have a pair of 4s, which means a 4 can be rooted out. I have a pair of x's, which means an x can be rooted out. Likewise, I know that -1 can be broken down into I and I, which means additionally an I can be rooted out. So I have an I, a 4, and an x. These being accepted constants, I'm going to say 4I followed by my variable. Perfect. That's an alternative way to write it. This is to utilize the root symbol each time. This is to go for bases and say, I'm not caring what the square root of 49 is. I want to find bases. And this will help you if perchance you don't spot the roots immediately. So let's say with this one, I don't spot the roots immediately. I say I have a -1 and a 300. I say I have a 3 and a 100. I don't recognize that this is a perfect square. Let's say I continue to break it down into a 2 and a 50, a 2 and a 25, and I say, hey, I recognize that the 25 is a 5 and a 5. Well, what I can do is I can say, hey, I'm going to pull out a 2 and pull out a 5. Likewise, my I and my I, I'm going to pull out an I as well. And with my W's, 1, 2, 3, I'm going to pull out 2 W's. Now, unfortunately, I didn't pull everything out. I still have this 3 left behind, and I have this other W left behind. And what this means is that my 2, my 5, my I, and my W all come out. My 3 and my W get left behind. Then I simplify what I can. 10IW square root 3W. This is what we call the split factors. Boop, boop. 2 and 2, because they're at 2 different spots on the tree, they'll root together to make a square root of 2. I could have alternatively done this question. Let's say I take the square root of negative 300, W cubed, and I do it like we did in number 3. And I say, okay, that's the square root of negative 1 times the square root of 300. That's the square root of 3 times the square root of 100. This is going to be the square root of W squared and the square root of W. I know that I can break down 3 of these roots. That's going to give me an I, that's going to give me a 10, that's going to give me a W. I have to leave behind the 3 and the W. In this case, I have a 10IW square root 3W. Either way that you do this, with the split factors, where you circle pairs of numbers, or if you just recognize where your perfect squares are, you can do either way. So what I want you to do is I want you to try out number 9 and number 11. I want you to pause the video, give them a shot, resume it when you're done, and see how you did. Okay, let's see how we did. So the first way I'm going to show using the traditional method. I'm going to say right here I have the square root of negative 1 and the square root of 25. Right here I have the square root of x squared because squared and squared will make x to the 4th, and the square root of y squared. All of which, 1, 2, 3, 4, and 5, I can root. Square root of negative 1 is I. Square root of 25 is 5. Square root of x squared is x, x, and y. If I reorganize that, I have a 5ix squared y. Perfect. The second one, because I don't know the square root of 160, I'm going to break this down according to the split factor tree. I get a negative 1 and a 160. I get a 2 and an 80. I get a 2 and a 40, 2 and a 20, 2 and a 10, 2 and a 5. I have 1, 2, 3, 4, 5, 1. Okay? So I have 1, 2. It's going to come out. 1, 2 that's going to come out. Oh. And I know right here, I know an I is going to come out. I left behind a 2, a 5, an N, and a Z. So if I rewrite that, I have I times 2 times 2 times N times N. Left in the square root, I have 2 times 5 times N times Z, which is going to simplify to 4in squared, square root of 10nz. And there we go.